We've learned how to differentiate functions, but what if we want to go backwards? What if we already have the derivative and we want to find the original function? Well, that's going to be the starting point of the second half of calculus. The first half is frequently called differential calculus, and it's all about derivatives. The second half is called integral calculus. We're going to start off with some definitions, though. First of all, we have this term antiderivative. Say a function f of x, capital F of x, is an antiderivative of little f of x if the derivative of capital F is little f. And this is a frequent notation that's used with antiderivatives. If you're talking about the antiderivative of some function little f, a lot of times people will use the capital of that. That's not a hard, fast rule, especially if you start off using the capital letter for your function in the first place. But you'll see that fairly often in some of the things people do with these things. But we'll actually have another notation for it in a moment. One thing to note is that antiderivatives are not unique. So if you have a function that's differentiable, you can differentiate it and you'll always get the same answer. Maybe it'll be a slightly different form, but you can always at least do some algebra to put it into the same formula. That's not true with antiderivatives. Take, for instance, let's say little f being 3x squared. You might recognize this as the derivative of the function x cubed. If you differentiate x cubed, you get 3x squared. That means x cubed is an antiderivative of 3x squared. But there's other antiderivatives as well. Take, for instance, capital G of x is x cubed plus 1. When we differentiate x cubed plus 1, the 1 goes away. And we're just left with the derivative of x cubed, which is 3x squared. So differentiating g gives us little f. Or we could even say h of x is x cubed minus 100. Use a different number there instead of plus 1. We get the same result. However, we are lucky enough that once we have one antiderivative of our function, then every antiderivative looks like, or shouldn't use little f. No, let's use capital F again. Will look like x cubed plus c, where c is some constant. In fact, this is you could say even a theorem, though the book doesn't actually express it as such. If capital F of x is an antiderivative of little f of x, then every antiderivative looks like capital F of x plus some constant. Now, of course, any constant here is actually going to give us a different antiderivative. So this whole process of reversing differentiation produces a whole infinite family of functions, but they are all the same up to adding on a constant. You have f of x plus 1, f of x plus 2, so on, so on, so on. They're all different functions, but they're all very, very similar to each other. We're going to denote this family of functions, this family of antiderivatives, like this. We call this the indefinite integral. And the process of finding these antiderivatives will be called integration. I'll explain why we call this the indefinite integral later on. For the moment, we might even just kind of just call it the integral, but there is another type of integral that we'll be talking about a little bit later, and we'll actually come at it from a slightly different perspective. This symbol at the front, this is kind of an elongated S. In fact, that's where the symbol comes from. It is an S that's been elongated. Again, I'll explain why it's an S later on when we talk about definite integrals. We won't see that for a few sections. We'll call it the integration sign. The inside, this f of x, we call that the integrand. The plus c at the end, this can be any constant. We'll usually use c for it. Technically, you could use a different letter if you wanted to, but it is very, very standard to use just a plus c at the end. We could call it the integration constant. But this is going to be our notation for these as we go forward. Think of this as the counterpart to d over dx of like x squared is 2x, where instead of being in order to actually write the x squared and its derivative in one line, we have this operator on the function. Here, instead, we use our integration sign with a dx at the end. This is actually a lot more common than writing things this way. We don't really have a notation for just say this is similar to the prime notation. We don't have a if f of x is 3x squared, then f with some notation equals x cubed for the integral. We always use this integration sign notation. Of course, the whole idea here is that integration and differentiation are inverses of each other, and that we can actually write that down as kind of formulas. So if we have the integral of a function, and then we differentiate that integral, I mean, this has a plus c in it, but the derivative gets rid of the plus c, and we just end up with whatever the integrand was. The other way around, we could take the integral of a derivative. If we differentiate a function and then integrate it, well, we get the function back, but we might not get the original function back. We might have an extra constant added to it. So we don't necessarily result in a complete inverse of each other. It doesn't always just completely cancel each other out. But we've actually seen that kind of thing happen before. Take the square function. If we take the square root and then square it, we do get the original number back, as long as we can actually put our number into the square root. But the opposite is not true. If we take the square of a number and then take the square root, well, if the number was positive to begin with, well, we will get back that same x. But if it is negative, then we get the positive version of it. So it's not exactly the x that we started with, but it's not too far off. It's either x or it's negative x. Well, here, we have f of x still in there, we just might have an extra constant added to it. Kind of a close enough of an inverse operation. Since integration is the inverse of differentiation, we do get a lot of properties of integration directly from it. For instance, we have rules for multiples and sums. So the integral of some number times a function, if we multiply our function by 2, for instance, what does it do to our integral? For differentiation, we were just able to pull out those constants and just deal with the derivative of the function itself. We can do exactly the same thing here. Any constants can just be pulled outside. In fact, I'll do that all the time. I'll just pull out constants that I don't want to have to deal with when I'm actually doing the integration part. We take a sum, or really we could do sum or difference, even though the difference can be taken care of by using a negative one in the first formula. then we can just do this term by term. We do not have to integrate both those at the same time. We can integrate them both separately and add the results together. Add or subtract the results. So just like we were doing with differentiation, for instance with polynomials, we were able to take each term by itself, kind of ignore the constants, and do the differentiation for the powers, and then put the constants back in, add them all together. We can do exactly the same thing here. Well, speaking of polynomials, let's take a look at powers. Can we get a power rule for integration? Well, remember, we are starting with the idea of differentiation. So what if we differentiate a power? We have our power rule for differentiation, where we take that power. I'm going to use an m here because I'm going to have to switch it out for a different letter later. You'll see what I mean by that in a moment. But if I differentiate x to the m power, I bring down that m in front, and then I subtract 1 from our power. I want to turn this around into an integration formula. Essentially, if the derivative of this equals this, then the integral of this one over here equals this. At least up to a constant. It's going to be x to the m plus some constant. Now the m here is a constant. So I can use my first formula and pull it out. And actually just divide it on both sides. The integral of x to the m minus 1 dx is going to be 1 over m x to the m plus some constant. Now, note that the constant here is completely arbitrary. Technically, these two c's are different constants. I had to divide the c here by m. But since it's completely arbitrary and I don't really care what it is right at the moment, I'm just going to call the new constant c as well. I kind of like to talk about that as like multiplying or adding or whatever with constants just kind of gets absorbed into the c. Basically, I don't want to be making up new c's as I go. Just call them all c's, and if I need to find out what the c is at the end, then I'll do that. We'll see a few problems where we have to find out what c actually is. But in general, if you're just adding a constant to this or multiplying this by a constant, just absorb it into that c. Okay, one last step here. I don't want to have m minus 1 in my formula. I just want to know the integral of x to the nth power. So I'm going to replace m minus 1 by n. Or in other words, m itself is going to be replaced by n plus 1. That means we'll have 1 over n plus 1. We'll have an x to the n plus 1. And we'll still have that plus c at the end. Say this is our power rule for integration. Basically, you're taking the integral of a power, you end up adding 1 to the power. It's the opposite when we differentiate, when we have to subtract 1 from the power. And then we divide by the new power. Instead of multiplying by the old power, we're now dividing by the new power. So everything kind of is opposite what it was before. And that can throw a lot of people off. You kind of have to get used to which one we do where. With integration, we add 1 to the power, and then we divide by the new power. While this formula does work for many n, such as things that are not even integers, it does work for n equals 1/2, n equals 1/3, so we can handle squares and square roots and cube roots. The formula does break for one particular number. Specifically, if I were to try to put n equals -1, this fraction out in front would be trying to divide by 0. The formula just completely breaks. So we're going to have to actually exclude -1 for the moment. Now, there is a way to handle n equals -1, and we're going to fill in that gap in a couple sections. Personally, I would actually just go ahead and fill it in right now because we do have the ability to do so, but the book actually puts it off for a while. So I'm going to follow the book structures, and we'll get to wait to fill in that gap. So for the moment, we have one little hole where we cannot put n equals -1. Note that the power rule does work even for n equals 0. N equals 0 is a special case. Let's kind of go ahead and put it in here. I don't want to make a new page just for this. But say we want to integrate x to the 0th power. Well, x to the 0th power is 1. This is really just the integral of 1 dx. And by our formula, we raise the power by 1. So we have x to the 1, but then we divide by that new power of 1. So dividing by 1 is the same as multiplying by 1. Or in other words, we just have x plus c. The integral of 1 is x, or x plus a constant. If we use our first property here and try to multiply that 1 by any constant k, we just end up getting k times the x that we have. So the integral of a constant is a linear term. So we're kind of writing this as an extra rule just because a lot of people don't like to think of constants as 0th powers, but they are. They do follow that same rule. But if you don't want to think about it every time like that, then we can just remember this as a whole nother rule. The integral of a constant is just that constant times x plus some arbitrary constant c. Now this video hasn't really been that long, but I do want to go ahead and split it up. We're going to work on some examples in the next video. So I'll see you there.